So how can they do something like that? You have a black box, basically. You have a black box, and you have no idea what is inside the black box. You know what it does. You don't know how it does it. So how do you find exploits in a black box?
Try different cases.
Try different cases. Very good. But there are so many different ways you can try. So they need some kind of tools to do it. And to use the tools, they need to understand how programs work. Okay? In other words, whoever attacked these, whoever wrote the Stuxnet intended for this purpose, or whoever discovered the 4 zero-day exploits, one, have very good tools. The tools that I'm talking about are tools that can look into the memory of a process, which is a program in execution, and see how it is used. So that's the first kind of tool that someone can have to use in order to discover exploits. The second thing, once you can identify, okay, this is the region of memory used by this particular program when it's executing, then you can start probing. Okay? Then you can say, okay, how can it interact with the external world? Most programs, especially these days, they interact with the external world by networking. Okay? It may not be networking like actually networking with another computer, but a lot of times the Windows surfaces themselves are quote-unquote network surfaces. It's just from the same host, so it doesn't generate any networking traffic on the network card. So then you try to probe it. But what do you do when you probe it? You look at the RPC, you look at the specification of the protocol. If the protocol says this header section should only be up to 255 bytes, guess what? These hackers will try to feed it like 1,000 bytes for the header, and see if the memory region, gets any significant changes. So that's how people attack proprietary software, even though it is a black box. With the proper tools, you can actually quote unquote get an X-ray vision of the program in execution. And when you can see a program in execution, how memory is allocated, overwritten, and so on and so forth, to the experienced hackers, they can use that information and at least formulate ways to at least probe the software. And once they probe the software, they can look for security holes, like, when I do something like this, it should not be overwriting this part of the memory space, but it did, or something along that line. So those are the things that people use to find zero-day exploits. And sometimes it's all software, and other times it is hardware assisted. In other words, you have to install a specific card or have a specific type of system in order to get this type of work done more effectively. But those people, the hackers, could not have done anything like that unless, one, they are very good programmers to begin with. They fully understand what is going on when a program executes, and three, they need to think out of the box, because they need to say, okay, these are the intended use of the computer. These are the specifications of the communication protocol, and what they're thinking is, how do I break it? Okay, so it's thinking out of the box. These hackers need to think out of the box in order to find the exploits, which brings us all the way back to this class. Okay, do you see any classes in ARC that will teach people how to hack? The ethical hacking class is not of that nature. The ethical hacking class is more like an exposure to things that people have done already. How do you protect your own system? But how do you write your own virus? How do you write your own worm? Do we have classes like that? No. Do you think a 4-year university in the States will have classes like that? No. Why? Why not?
Mass hackers. Mass hackers. Hacking is illegal.
Hacking is illegal, okay, but it only applies to software that is already copyrighted. The DMCA, the Digital Millennium Copyright Act, specifically says that if a software is copyrighted and it has copy protection mechanisms, any means to try to bypass the copy protection mechanism is illegal. Now, if I wrote my own program, okay, if I wrote what we call a honeypot program, basically a target to be hacked, and I use that as an example, and I use my own technique to hack my own program, that it's not breaking the law at all. So that's perfectly fine as far as legally, it's definitely fine. Most people don't want to get into this because they think it is controversial. Okay, do we actually want to train people to become hackers? The question is,
They do, of course.
if we don't, does it stop other countries? Does it stop other organizations outside of the United States? No. But if we don't have hackers or people who can think like hackers, how do we defend against people who are, actual hackers? That's the question, okay? So I think it is appropriate and it is a necessity to teach how to hack in terms of from the programming side. How do you write programs that cannot be hacked? And if you want to target something, how do you hack into the other program? I think those are, topics that should be introduced, maybe not at a community college level because it does require a lot of understanding of how programs work, how operating system work, and assembly language programming. But maybe at a 4-year university, I think they should have classes to look into that sort of thing. So anyway, that's all I want to bring up, before the actual core of this class. When you guys take assembly language programming, we'll talk about some of these concepts again, because that class is basically the first baby step to gain certain X-ray visions into how a program works when the program is in execution. Okay, so let's just move on now, to go back and talk about the more boring stuff. But the boring stuff is necessary. Without understanding the boring stuff, we can't get to the not so boring stuff. So we're back to top-down design. Computer's sleepy today. And let's see. So last time did we do it? Have we done? Have we done this part? Nope. Okay, so let's go ahead and get started with this one. So I'm not going to use this. I don't want to read from my own notes. So what I'll do is I'm just going to capture the notes using a text file. And let's go ahead and start a folder for today. 10:08. This is my only class today, so I don't really need to write down the class number. I think last time we talked about an example, okay? And I basically picked a really large number for you guys to factor to force you to use a systematic way to find factors. Okay, so let's just kind of go back to that one and try to determine, how do you find all factors of a particular number. Okay, let's try something easy first. Okay, let's try 65. What is a prime factor of 65? 5 is 1. So 65 is 5 times 13. And how about 13? What is a prime factor of 13? 13 is its own prime factor. And by the time we get to 1, we can stop. Why can I stop when I get to 1? Because 1 is not even a prime number itself. Okay? 1 is not even a prime number. By definition, it is not a prime number. Okay? So here's one example. We can try, some other examples. Like 125. 125 is what? 5 times 25. And then 25 is 5 times 5. And 5 is 5 times 1. So we can identify all of these, prime factors, 5, 5, and 5. The next question is, now that we seem to have a systematic way of doing things, can I capture that method into an algorithm? That becomes the next question. This part is also the most difficult part to teach, because I'm trying to teach, how to design an algorithm. The execution of a conditional statement is easy because it is just a rule. If the condition is true, you go for the then branch. If the condition is false, you go for the else branch, and that was it. Even the pre and post conditions are easy because we have rules to determine when to use a substitution rule, when to use a forget rule, and it's just a mechanical way to look at the precondition and derive the post condition. This part is very hard to teach because there's no rule to follow. There's no template to follow. Okay? It's basically how do you make something? How do you come up with a solution? So I can only teach it in a way that, in a way that is kind of really step by step. Okay, so each time or for each step, we only add or we only introduce a little bit of logic into it, and we'll just try to evolve the algorithm this way, slowly, step by step, into its final form. Revision 1. Okay, the first thing I usually ask myself is this a loop? In other words, am I doing something repetitively? If you just look at 2 examples, before the separator line, am I doing something repetitively, again and again?
Yes.
Okay? So that implies that we need what kind of control structure?
Loop.
A loop, very good. So at this point, we have identified that we need some kind of a loop. And the way I identify that we need some kind of a loop is loop and loop. It does not say it is a pre-checking loop. It does not say it's a post-checking loop. All it does is to say we need some kind of a loop. So I'm not being very specific here. All I'm saying is we need to do something again and again. Do we want this loop to be an infinite loop? In other words, do we want to get out of the loop at some point?
Yes.
We do, huh? So when do you exit the loop in these 2 cases?
When the one should be the number you should.
Factor.
Yeah.
Okay. Good. Okay.
I was thinking the loop would be inside of this loop.
Okay. We don't want to deal with a loop inside the loop at this point, and that was the whole point of top-down design.
That's right.
Yep. Okay. So we'll say that loop, and I won't even try to use any variable names. I'll just say that exit the loop when the number to factor is 1. That is really not very much pseudocode, is it? But it's okay. If this is our first revision, we'll just use something that fuzzy. The second revision is try to be, I want to be more specific. In other words, the number 2 factor, if you put a double quote here and a double quote here, is kind of long. I don't want to use, that kind of a, expression or reference when I refer to a particular thing that I use in an algorithm. So in revision 2, we'll just say let n be the number 2 factor. Okay? So with that assumption, with the introduction of the variable n, my loop can get a little bit more concise, because when I say the number to factor is 1, hey, that's the same as just saying n is 1. Okay? Is that okay so far? So in revision 3, we have to look into the loop itself, and we ask ourselves, what exactly are we doing per iteration? In other words, we are trying to backfill the content of the loop here and ask ourselves, what are we going to do per iteration? You have to go back to the example. What did we do per iteration? In each step, we look for a particular prime factor of the number n, right? And then we identify that, we can optionally print it out, and then we change n so that for the next iteration, n is smaller. Because it went from 125, n equals n25 in the first iteration. In the second iteration, n becomes 25. In the third iteration, it became 5. And if I had a fourth iteration, it would have been 1. Yep.
Would you also want to start factoring at 1 plus half of the number, because there couldn't be a factor bigger than that?
We'll deal with that stuff later. Okay, so we'll start with something that's vague first. Okay, we just want to identify what we want to do. We will worry about how to do it later. Okay, so within the loop for each iteration, the first thing we want to do is to find a prime factor f of n.